Hello, I'm Tongjai Yampaka. I will introduce the high-performance concept with GPU using CUDA. Driven by the market demand for real-time, high-definition 3D graphics, the Programmable Graphic Processor Unit, or GPU, has evolved into a high-parallel multi-thread, many-core processor with computational power and very high memory bandwidth. The reason behind is floating point capability between the CPU and the GPU is specialized for highly parallel computation. GPU designs small transistors and devote to data processing rather than data caching and fault control. This concept works for highly parallel computations because the GPU can hit memory access latencies with computation instead of avoiding memory access latency for large data cache and fault control. Data parallel processing maps data elements to parallel processing threads. Many applications that process large datasets can use a data parallel programming model to speed up the computations. In 3D rendering, large sets of pixels are mapped to parallel threads. For example, image and media processing applications such as post-processing of rendering images, video encoding and decoding, image scaling, stereo vision, and pattern recognition can map image blocks and pixels to parallel processing threads. In fact, many algorithms outside the field of image processing are accurate by data parallel processing, such as physics simulation, computational in finance, or computational in biology. In November 2006, NVIDIA introduced CUDA, a general-purpose parallel computing platform and programming model that leverage the parallel compute engine in NVIDIA GPUs to solve many complex computational problems in more efficient way than CPU. CUDA is a software environment that allows developers to use C++ as a high-level programming language or other language. CUDA is designed to support various language and application programming interfaces. The advent of multi-core CPUs and many-core GPUs mean that mainstream processor chips are now parallel systems. The challenge is to develop application software that scales its parallelism to relevate the increasing number of processor cores, such as 3D graphics application scales their parallelism to many core GPUs with wide number of cores. At its core are three key abstractions: the first hierarchy of thread groups, the second shared memories, and the last variant synchronizations that are simply exposed to the programmer as a minimum set of language extensions. These abstractions provide fine-grained data parallelisms and thread parallelism. They guide the programmer to partition the problem into sub-problems, can be solved independently, in parallel by block of threads, and each sub-problem can be solved in parallel by all threads within the block. This decomposition preserves language by allowing threads to cooperate when solve each sub-problem, and at the same time enable automatic scalability. Each block of threads can be scheduled on any of the available multiprocessors in a CPU, in any order, concurrently or sequentially, so that a compiled CUDA program can execute on any number of multiprocessors. GPU is built around an array of streaming multiprocessors. Multi-thread program is partitioned into blocks of threads that execute independently from each other, so that a GPU with more multiprocessors will automatically execute the program in less time. The main concepts behind CUDA programming divide into two parts of code. The first, serial code, executes CPU thread. It's called host code, and parallel code execute in many concurrent GPU threads across multiple parallel processing elements is called device code. As mentioned in heterogeneous programming, the CUDA programming model assumes a system composed of a host and a device, each with their own separate memory. Kernel operates out of device memory. The runtime provides functions to allocate, deallocate, and copy device memory, as well as transfer data between host memory and device memory. And the next shows details of CUDA architecture. GPU can handle thousands of concurrent threads. CUDA programming model supports even more, allow a kernel launch to specify more threads than the CPU can execute concurrently, and helps to optimize kernel launch time. The threads are grouped into blocks, and blocks are grouped into a grid. A kernel is executed as a grid of blocks of threads. CUDA allows programmers to define functions called kernel that, when called, are executed n times in parallel by n different CUDA threads. A kernel is defined using the global declaration and the number of CUDA threads execute the kernel. For a given kernel is specified using a new bracket. Each thread executes the kernel given a unique thread ID. As an illustration, the following sample code using a built-in variable thread IDX add two vectors A and B, size n, and store the result into vector C. Here, each of the n threads execute vec_add function by one pairwise addition. For convenience, thread IDX is three-component vector, so that thread can be identified using one dimension, two dimension, or three dimension by thread index, forming one dimension, two dimension, or three dimension block of text called a thread box. This provides natural way to invoke computation across the elements in a domain such as vector, metric, or volume. There is a limit to the number of threads per block, since all threads of block are expected to reside on the same processor core and must share the limit memory resource of that core. On current GPUs, a thread block may contain up to 1024 threads. However, a kernel can be executed by multiple equally shaped thread blocks, so that the total number of threads is equal to the number of threads per block times the number of blocks. Blocks are organized into one dimension, two dimension, or three dimension grid of thread blocks. The number of thread blocks is a grid. It's usually dictated by the size of the data being processed, which typically exceeds the number of processors in the system. Each block within the grid can be identified by one dimension, two dimension, or three dimension unique index accessible within the kernel. Through the built-in block IDX variable, the dimension of the thread block is accessible within the kernel through the built-in block dimension variable. A thread block size of 16 times 16, 256 threads. Although ability in this case Each common choice, the grid is created with enough blocks to have one thread per metric element as before. For simplicity, this example assumes that the number of threads per grid in each dimension is evenly divided by the number of threads per block in that dimension. That need not be the case. Thread blocks are required to execute independently. It must be possible to execute them in any order, in parallel or in series. These independent requirements allow thread blocks to be scheduled in any order across any number of cores and illustrated by figure, enabling programmers to write code that scales with number of cores. Threads within a block can cooperate by sharing data across some shared memory and by synchronizing their execution to coordinate memory access. More precisely, one can specify synchronized points in the kernel by calling synthread inherit function. Synthread acts as a barrier at which all threads in block must wait before any allow to process. Shared memory give an example of using shared memory. In addition to synthread, the cooperative group API provides a rich set of thread synchronization primitives. For efficient cooperation, the shared memory is exists to be low latency memory near each processing call. The advantage of CUDA. CUDA has several advantages over traditional zero-purpose computation on GPU using graphic APIs. Code can read from arbitrary address in memory, unified virtual memory, unified memory, shared memory, CUDA approach fast, shared memory region that can be shared among threads. This can be used as user-managed cache enabling higher bandwidth than is possible using texture lookups, faster download and read back to and from the GPU, full support for integer and bitwise operation including integer texture lookup. They have some limitations. Copy between host and device memory may it cause a performance hit due to system bus bandwidth and latencies. Unlike OpenGL, CUDA-enabled GPUs are only available from NVIDIA. No emulator of fallback functionality is available for modern revisions. And next, I will show you how coding GPU when you don't have the real GPU. And now, I introduce you the Colaboratory. Colaboratory or Colab for short allows you to write and execute Python in your browser with zero configuration required. Free access to GPUs, easy sharing. Whether you are a student, a data analyst, or AI researcher, Colab can make your work easier. The document you are reading is not static web page, but an interactive environment called a Colab notebook that lets you write and execute code. You can click Plus Code for new cells, write your code, and click Play button for run your code. Click Plus Code. You can see the new cell and write your code. And then click the Play button for run your code. You can see the result in the below. Colab notebooks allow you to combine executable code and list text in a single document along with images, HTML, LaTeX, and more. When you create your own Colab notebooks, they are stored in your Google Drive account. You can easily share your Colab notebooks with coworkers or friends, allow them to comment on your notebook, or even edit them. To learn more, you can see a view of Colab websites to create a new Colab notebook. You can use a file menu above or use following link create a new Colab notebook. Colab notebooks are Jupyter notebooks that can host by Colab. You can learn more about the Jupyter project see jupyter.org. TensorFlow with GPU. This notebook provides an introduction to computing on GPU in Colab. In this notebook, you connect to a GPU and then run some basic TensorFlow operation on both the CPU and a GPU, observing the speed up provided by using the GPU. You can enable and testing the GPU. First, you need to enable GPU for the notebook. You can navigate to Edit Notebook Settings and select GPU from Hardware Accelerator drop-down. Edit and Notebook Settings. You can see Runtime Type. You can select Python 3 or Python 2 and Hardware Accelerator. None is only CPU. And you can select GPU or TPU. Then you can save. And now you can look GPU version that Colab provides for free using NVIDIA SMI command. The results show GPU that Colab provides for you. Tesla P4 version and CUDA version 10.1. And then you can use not only Python but also C language on Colab. And you need NVCC for Jupyter environment installation. Okay, it's successful build NVCC plugin on your Colab workspace. Then you need load NVCC for Jupyter environment in your workspace. Okay, and now you're ready to write your GPU code. In this line, the global declaration, a kernel is defined using the global declaration, and this function do add each kernel value. And this line, in this line indexing the GPU array, just like the memory indexing or array indexing. Okay. And this function for using CUDA add vector in parallel. You need declaration at date on device T GPU array. Array def A is array A on GPU. Def B is device array on GPU array B. And device C is array C on GPU. And then allocate GPU buffer for 3 vectors, 2 input A, B, and 1 output is C. Using CUDA memory allocation command syntax. And copy input vector from host memory to GPU buffer. Using CUDA memory copy def A Def A is array A on GPU and A is array A on CPU. This function copy array A from GPU to array A on GPU and launch a kernel on the GPU with one thread for each element. The number of CUDA threads execute the kernel. This line call one block and 5 threads per block. CUDA device synchronize, wait for the kernel to finish and return the results or any error. And now, copy output vector from GPU buffer to the host memory using command CUDA memory copy. Copy only the result array C. The result from array C on GPU to array C on CPU. Using CUDA memory copy device to host and CUDA free def C, def A and def B is a command to release the GPU array. And now call the main function. Define input variable array A, B, and C. A, B, A and B are the input, and C store the output. And call GPU function. And now show the results. You can print the result in the host or in the CPU. And CUDA device reset is reset the device. Okay. The below show the results for this course. This video explains simple how program the GPU, and I think this video can help your work. Thank you for your attention.